Students. Today we are going to discuss about the summary of vsepr theory and bond polarity and Kazan story. Okay, let us start. I know that you have already watched one video based on vsepr theory. So I'm only giving you the summary of vsepr theory. So for what we are learning vsepr theory, we are learning vsepr theory in order to understand the shape of a molecule. And in vsepr theory, it depends upon the number of pair of electron present in the outermost shell of the central atom in the molecule. Okay, and there will be two type of pair of electrons. One should be bonded pair of electron, one should be free. That is called a non-bonded or lone pairs. Okay. And if there is lone pair in the outer shell, it's very difficult. The repulsion will be more. So it will be staying at maximum distance from the bond pair. In such condition, what will happen? The bond pair will come close together, staying the lone pair at maximum distance. And in this case, one more thing is there. If double bond or triple bond is present, we will consider it as one single lone pair. Sorry, bond pair. Okay. For example, let us see the case of carbon dioxide. If you take the case of carbon dioxide, we know that here there are double bonds. Okay. But we are treating it as one bond pair. Here, one bond pair. Here, so total two bond pair. So if two bond pair are there, they will stay at maximum distance, and so it is having a linear geometry with a 180-degree bond angle. Okay. And if you have two or more resonance structure, we can apply vsepr theory in any one of the structure. Okay. So now let us move to the next thing. That is, we already discussed lone pair is there. The lone pair repulsion will be greater than lone pair bond pair repulsion, and which in turn is greater than bond pair repulsion. So if lone pair are present, bond pair will come close together. It will shrink and the bond angle will decrease. Okay. Now it is better if you are learning the vsepr theory in this way. So here, if there are no lone pair, we can learn the molecule in this way. So if there are no lone pair, this is the case if there are no lone pairs. Okay. So AB2 type. AB2 type means there is only two bond pair, no lone pair. Okay. BeCl2 is an example. If you take BeCl2, the Cl atom will stay at maximum distance like this linear manner, and its bond angle should be 180 degree. In the case of AB3 type, means central atom with the three bond pairs. Okay, three bonded atom, three bond pairs, no lone pairs. In such a case, the atom will be staying at maximum distance here, and it must get a shape of a trigonal planar shape. Okay, BF3 is an example for that. Okay, BF3. So its bond angle should be 120 degree in this case. And if it is having an AB4 type molecule, AB4 means 4 bond pairs only. So we will get a tetrahedral shape, and the bond angle will be 109.5 degree. Okay, CH4, NH4 plus, important example for this AB4 type molecule. Okay, if you have an AB5 type molecule like PCl5, it is having a trigonal bipyramidal structure. Okay, trigonal bipyramidal structure, but you have to understand the bond angle is different. In the inside the triangle, it is having 120 degree bond angle, and here, since it is perpendicular, its bond angle will be 90 degree. And also you have to look at the bond length. The bond length will be more on the axial position compared to the equatorial position. The reason for that is the bond pair in the axial position will be suffering more repulsion from the equatorial position. So it will stay at maximum distance. Okay. And there are AB6 type of molecule. AB6 type of molecule, what will happen here? It is having a octahedral geometry. Okay. And all the bond angle will be 90 degree. Okay. Like this. And A, B, B, B. And up and down, like this. Now let us see the case where there is lone pairs. Okay. And look at this case. Here lone pairs are present. So the first case is AB2E. AB2E means two bond pair and one lone pair. So 2 plus 1, 3. As a total 3 pair of electron is there. So we will expect a trigonal planar geometry. But this lone pair we cannot count, right? The lone pair here we cannot count. So the shape will be bent. And the lone pair, if you look at the lone pair also, it will be staying at maximum distance from the bond pair, and the bond pair will come very close together. So what we are expecting is 120 degree, but it will be shorter than 120 degree, 119 or 118 degree it will become. Okay. And in the case of AB3E type, 3 plus 1, 4. Okay, 4 bond pairs we will for a pair of electron, 3 bond pair and 1 lone pair. So we are expecting a tetrahedral geometry, but since there is one lone pair, what will happen? This part we cannot see, and the geometry of this part is trigonal pyramidal. NH3 is a very important example of that. And another type is AB2E2. So here also 2 plus 2, 4 is the total number of pair of electrons. So we will expect again tetrahedral geometry since there are two lone pairs. This part we will see, and it is having a bend shape. Okay, water is an example. So in this case also, because of the lone pair of electron, the bond pair will come close together. So this question many times they asked, okay, why the bond angle is less? Because the reason is actually we are expecting 109.5 degrees. Since the bond pair come close together, it become 107 degree. Okay, here also in water molecules still there are two lone pairs, so it will come very close together than this. Okay, so the bond angle will decrease almost to 104.5 degree. Okay, so it will decrease like that. And next case, AB4 E type means E means lone pair, 4 bond pair and 1 lone pair. E is lone pair. Okay, so in this case we are expecting 4 plus 1, 5, so trigonal bipyramidal shape. Since there are one lone pair, it will stay at maximum distance from other bond pairs. So this position give less repulsion compared to any other position. So this part, the shape is called a seesaw shape, and SO4 is an example for that. And let us see the case of AB3E2 type. In this case also 5. So we are expecting trigonal bipyramidal, but there are two lone pairs, and that two lone pair will stay at maximum distance here, away from the other bond pairs. Okay, so the shape here is T shape. So we are getting a T shape for this type of molecule. And another important type is AB5E. Example is BRF5. And here we are expecting 5 plus 1, 6 octahedral, but since lone pair is there, what will happen? A square pyramidal shape we will get. Okay. And another one is AB4E2 type, 4 plus 2, 6 again. And that 2 will be at axial position. That is the maximum distance, right? So here we will get a shape of square planar. XAF4 is an example for that. Okay, now let us see the polarity of the molecule. Okay, so we already know that a covalent bond is not completely pure covalent bond. It is having some ionic character. Just like that, ionic bond also is having some covalent character. So first we can see partial ionic nature of covalent bond, polarity of a bond. Okay. So in this case, see, if a molecule is formed from same atom, so same atom means what? Example for that is hydrogen. So it is, this bond is formed from same atom. So we know already what is electronegativity. What is electronegativity? Electronegativity is the tendency of an atom to attract shared. This is a shared pair of electron towards it. Okay, that is called electronegativity. So if you take the case of hydrogen, these two hydrogen is having same electronegativity. If there is same electronegativity, what will happen? The molecule will be will not be polar, it should be non-polar. Okay, so all homonuclear diatomic molecules should be non-polar. Okay, so example is Br2, Cl2, F2, H2, N2, all these are example. Okay, so in this case, we can see that the bond is also non-polar and the molecule as a whole is also non-polar. Now, let us take the case of diatomic molecule in which it is bonded with a different atom, hydrogen and chlorine. Okay, so we know that chlorine is more electronegative than hydrogen, so it will get a partial negative charge. More electronegativity means the shared pair of electron will be more towards this chlorine, so it will get a partial negative charge and it will get a partial positive charge. Okay, since there is charge separation, it should be polar. Okay, so always all heteronuclear diatomic molecules should be polar. Okay, now if you are taking a molecule, for example, CH4. Okay, in this, the carbon atom, this is a central atom, it is connected with the 4 other atoms. But here, what is the condition? All the atom must be same. All these atoms must be same. One condition, all the atom, same atom. And the carbon is having no lone pair. The central atom is having no lone pair, another condition. In such a condition, it should be always non-polar because all the bond dipole will cancel. Okay, that is the reason. Now, a molecule is having a lone pair of electron. That example we already learned, NH3, it is having a lone pair of electron. The geometry is pyramidal geometry. All the molecule which is having a lone pair of electron, okay, should be always polar. Here, so if a molecule is formed from same atom, that should be non-polar. And if a molecule is formed from different atom and the central atom is bonded to same atom and not lone pair of electron, that would be non-polar. Diatomic heteronuclear molecule should be polar, and also a molecule having lone pair of electron should be also polar. Okay. Now, if the bond will be polar if there are difference in electronegativity between bonded atoms. We already discussed HCl case, right? In the case of HCl, this bond is polar because there is difference in the electronegativity. If there is a difference in electronegativity, that will give a dipole moment to the molecule. Okay, because there is charge separation between them. Two equal and opposite charge separated by a small distance, right? So it will give a dipole moment. Since the unit of dipole moment is diphi, so there will be a dipole moment between this atom. Okay, so because equal and opposite charges are separated by a small distance. Okay, in the case of non-polar molecule, what will happen? That dipole moment will be 0. If the dipole moment is 0, that molecule will be non-polar. In the case of a polar molecule, the dipole moment will not be 0. This dipole moment is having, it is a vector quantity, it is having both the direction and magnitude. So direction is important. If the dipole moment is having a value and it is acting on opposite direction, what will happen? That will cancel each other and you will get 0 dipole moment at the end. Okay. So let us see a few cases. These are few cases, very important cases. This is the linear molecule. Look at this linear molecule. Already we discussed that if central atom is not having lone pair and it is connected with the same atom, it should be non-polar. What is the reason? Because if we look at BeCl2, what happened? Be, if we are comparing the electronegativity, Cl is having more electronegativity. So the bond pair will be actually dragging towards chlorine. So that is the direction of dipole moment here. We can put an arrow like this. So this is the direction of movement of this bond pair, and here this one. Okay, so what will happen? Actually, the dipole moment, I already said, it is having both the magnitude and direction. So it will cancel each other because it is acting on opposite direction. So the total dipole moment at the edge should be 0. Okay, so that is the reason why if the molecule is, the atom attached to the central atom is same, what will happen? Finally, the dipole moment becomes 0 and this become non-polar. But see the same linear case with the two different atoms. For example, BE, one is Cl and one is F, suppose. So its electronegativity should be different, okay? So the magnitude of dipole moment should not be same here, right? So it will never cancel each other. You will get, it will cancel, but you will get a dipole moment because the values are not same, okay? So that must be polar, okay? And another case is bend. Bend molecule, we learned those with lone pair of electron, those with the lone pair of electron. Two cases we learned, right? In the case of O3 also, there is a lone pair of electron. And in the case of water, not water, ammonia, there is a lone pair of electrons. So if there is lone pair of electron, what will happen? The bond dipole will not cancel each other and there will be a net dipole moment at the end and that will be polar. And trigonal planar, all these atoms are same. So we know that it is non-polar already. How it is non-polar? Because there is lone pair, there is dipole moment on these two direction, but here also a dipole moment is there. So this, if you are taking these two, resultant we will be taking resultant dipole moment. If you take that, will be on the opposite direction. So it will cancel each other, okay, and it becomes non-polar. But if it is attached with another atom, okay, a different atom other than X, what will happen? This bond dipole will be different from these two, okay? So it become polar because all the dipole moment should not cancel. Dipole moment should not be equal to 0, okay? Now let us see the case of tetrahedral. Here also all the bond dipole will cancel each other because all the atom attached should be same, okay? So the dipole moment should be equal to 0, so it is non-polar. But here one different atom is there, so the dipole moment should not be equal to 0 because the bond dipole bond cancels. But all these cases you can see there is a polarity on the bond, okay? Even though it is non-polar, the bond should be polar, okay? Because there is difference in the electronegativity between the atoms. Clear? Okay. Now, let us see some cases. We already seen all these cases, I think. Carbon dioxide. Carbon dioxide, we know linear molecule it is, and its bond dipole is acting on different, opposite direction, right? So since it is acting on different direction, the total net dipole moment becomes 0 and it is non-polar. But in this case, we have a lone pair of electrons. So since there is lone pair of electron, the bond dipole won't cancel, okay? There will be a net dipole moment. So it is polar. In this case, I said already heteronuclearity. So always there will be a charge separation and it should be polar. Okay. Now let us see another case. In this case, look at this. These three bonds are same, but this bond is different. Okay. This bond is different. This is attached with another atom. So the bond dipole, the resultant bond dipole, if you're taking that bond, cancel fully. We will not get a dipole moment equal to 0. So because of that, what will happen? It will be a polar molecule. Now let us see this case. Every time they're asking the paper. And in this case, see, they can ask you a question, why the dipole moment is very less for NF3 and it is high for NH3. The reason for that is, if you are looking at the bond dipole, see, fluorine is more electronegative than nitrogen. So the bond dipole, the direction is, this is the direction. And here the direction of lone pair, that is up. So what will happen? They will can opposite direction. So they will cancel each other bond dipole and we will get a less dipole moment here. So it is less polar compared to this. Here what happened? Hydrogen and nitrogen, if you are comparing, nitrogen is more electronegative than hydrogen. So the direction of bond dipole will be here. Okay. Will be towards this nitrogen. So that all these are in the same direction. So we will take the resultant of all this. So it is having a dipole moment value, higher value. So it is more polar than this. Okay. Now, Let us see another case. Partial covalent nature. So far we were discussing about the covalent bond is having some ionic character because of partial okay, because of the difference in electronegativity. So far we discussed about HCl molecule, carbon dioxide, all these we know that all these are covalent bonds, but there are a difference in electronegativity between them. So they will get a partial positive and partial negative charge. So this will tend to be ionic little bit. So that is the polar nature, right? That's what we learned. Now we are going to learn about the partial covalent nature of ionic bond. If you are taking any ionic bond, it is having some partial covalent nature also. So that partial covalent nature depend upon few things. What are them? Smaller the size of the cation. So small size of the cation and larger the size of the anion. If smaller the size of the cation and larger the size of the anion, the greater covalent character it is having. Okay, smaller the size of the cation and larger the size of the anion. If you take lithium, it is having smaller size. Okay, and lithium bromide, bromine is having the size of the bromide is more right compared to fluoride and chloride. So if you take lithium fluoride and lithium bromide, who is having more ion covalent nature, this must be having, because it is having, lithium is having smaller size and bromide is having higher size compared to F minus. Okay, it's bigger than F minus. That is why it is having more partial covalent nature. Okay, so the greater the charge on the cation and the greater the covalent character of the ionic bond. Okay, so if you take lithium LiBr, and if you take MgBr. If you take both this, lithium is having +1 and magnesium is having +2 oxidation. So the charge will be more here. So what will happen? It is having more partial covalent nature than this one. Okay. So for cation of the same size and charge, the one with electronic configuration N minus, so the transition element. This is the electronic configuration of transition element. Is more polarizing. It should be. So those which is having transition element electronic configuration will be more polarizing than those with a noble gas configuration, NS2 and P6 configuration, alkali metal, alkaline earth metal, and also if you have the same electronic configuration. So for cation of the same size and charge, for the cation of the same size and charge, we will see the electronic configuration. Those which is having the configuration of transition metal will be more polarizing than those which is having the configuration of alkali and alkaline earth metals. Okay. So let us see the process of polarization, how it will happen. Look at this. In this case, this is a cation, this is an anion. So, according to Fajan's rule, what is happening? If larger the anion, it is very easy for the cation to distort that electron cloud towards it. Right? It is very easy. If suppose it is having more charge also, the dragging will be very easy from the anion. If it is having a more size, what will happen? It is having a big size, the electron cloud easily can distort. That is the reason why we are telling bigger the anion and smaller the cation. Smaller the cation means the nuclear charge will be more over smaller cation. So it can easily drag the electron towards it. So in this case, if the anion is big in size, what will happen? Its nuclear charge is less. So the outer electron will be easily, we can distort the electron cloud in the outer shell. Okay. So what will happen? Actually, the electron cloud is coming in between these two nucleus, right? These two nucleus. So that is getting a similar it will become similar to that of a covalent bond. In covalent bond, what is happening? Actually, what is happening? It is an attraction between a pair of electron, shared pair of electron and a nucleus. So the electron density will be in between the nucleus, two nucleus, right? So here also that is happening. When the electron is distorted here, the electron density is coming in between these two nucleus. So it will get some covalent nature. Understand? Okay. So as a summary, I can tell you. Ionic character, low charge on the ions, okay? Covalent, high charge on the ions, okay? It should have a small cation and high charge on the ion and a larger anion, okay? Valence shell electronic configuration should be same as D. Ionic means low charge on the ion, large cation and small anion, and noble gas configuration should be ionic. That is the difference. That is a summary of a Jan's rule. Okay, thank you.